A simple linear regression model is fit, relating plant growth over 1 year to the amount of fertilizer provided. 25 plants are selected, 5 each assigned to each of the fertilizer levels. The results of the model fit are given below. And we want to know if we can conclude that there's an association between fertilizer and plant growth at the 0.05 significance level. Okay. Well, we want to do this in a semi-rigorous way, but I don't really want to get into all of the nonsense about tables. Okay. So our null hypothesis here is that there's no association, right? We don't know if there's an association. The assumption is that there is none. So H naught is that beta 0 is 0. The alternative is that, I'm sorry, not beta naught, beta 1. Our alternative is that beta 1 is not 0. Okay? And when I talk about beta naught, I mean this number there. It's not that big. It wouldn't be weird if it was 0. Of course, 0.527 isn't 0, but is it statistically different from 0? It's the question we're asking here. Okay, well, if this data is normally distributed, then we would have some sort of model like this. We would have some sort of cutoff value where 5% of the data was in these two tails. So in this tail, because we're at a 0.05 levels of significance, half of that 5% is here. So this is 2.5%. And here is another 2.5%. And so we're looking for this value here. Okay. And I'm going to call it value V, because I want to talk a little bit about value V. If this model is normal, the cutoff value for 5% in a two-tailed test is approximately equal to 1.96. So that's for a normal model. And if you go to a table and you look up the Z score that corresponds to 5%, you'll find that that our cutoff value is 1.96. Now, if we want to ballpark it, 1.96 is pretty accurate, but usually we say it's about 2. Okay. Now, in this particular example, we've got N equals 25. We've got 25 plants that are selected. All right. Our model has one parameter, one variable X. So the degrees of freedom here are N minus P minus 1 over 23. Now, 25 plants leads us to believe that maybe we don't have enough data for this to be a normal model. Maybe we need this to be a model that uses the t distribution. So for t-distributed data, with 23 degrees of freedom, your v value would be, again, just ballparking it, much closer to somewhere between 2 to 2.5. It really doesn't matter what your n is. 2.5 will be pretty close as a value of v. So what this means, if you're just talking in general terms, if our error here is, or if our beta 1 is more than about 2.5 standard deviations away from 0, then we're going to reject the null hypothesis, because we wouldn't see a beta 1 value that far away from 0 very often. Okay. So it doesn't really matter what value of v you use. You got 1.96 you might use 2, you might use 2.5, you might split the difference and use 2.25. Whatever assumption you make, you have to put it in there. But in reality, we almost never get cutoff values that are that close to 2. So what's our cutoff value here? Well, if we look at our t, we get 5.386. That's the ratio of beta 1 over the standard error. Right? It's 5.27 divided by 0.098. So our beta 1 value ends up being more than 5 standard errors away from 0. So looking at this model, whether we're using a normal model or a t model, both with the same shape, our cutoff value, our t value, or our z value, is somewhere out here, 5.386. So again, let's talk about v. It could be 1.96 if we're using a normal model, could be as high as about 2.5 if you're using a t distribution with 23 degrees of freedom. In either case, 5.386 is well past the cutoff value. So what happens now? Well, we reject the null hypothesis. It's so unlikely to have a value of t that's value of beta 1 that's 5.38, 5.4 standard errors away from 0. So we reject H naught because beta 1 is about 5.4 standard errors away from 0. And so can we conclude that there's an association between fertilizer and plant growth? Yes, we can. So there is an association. Between fertilizer and plant growth.